given that Sn is equal to, let's say Sn is equal to 5 plus 5 square plus 5 cube plus we keep on adding all the way down to 5 to the n. This is Sn, right? So in other words, I'm going to rewrite Sn. I am going to rewrite Sn as the sum from r equal 1 to n of 5 to the r. That is Sn. In other words, Sn is the sum from r equal 1 to n of 5 to the r. All right, and they want us to show that, so they want us to prove, this is what they want us to prove. They want us to prove that 4Sn, so they want us to prove that 4 times the sum from r equal 1, 4 times the sum from r equal 1 to n of 5 to the r is equal to 5 to the n, 5 to the n plus 1 minus 5. This is what they want us to prove, that 4 times 5 to the r is equal to 5 to the n plus 1 minus 5. So let's go ahead and prove this, all right? Again, to prove this, you start with your 3 cases. You start with n is equal to 1, all right? When n is equal to 1, the left-hand side is going to be equal to the sum from r equal 1 to n, which is the sum from 1 to 1, all right, of 5 to the r, which this is just 5. So this is going to be 4 times 5. Another way to look at it is when r is equal to 1, this is it. N is equal to 1, it's just 5, just the first term. 4 times 5, which is 20. That's the left-hand side, all right? Then the right-hand side is going to be, the right-hand side is going to be, all right, now we have this now, right-hand side, put in 1, it's going to be 5 square minus 5. 5 square minus 5 is still 20, and so n equal 1 is true. So therefore, n equal 1 is true. N equal 1 is correct. So now we need to do is assume n equal k is true. That is step 2. Assume n equal k is true. So let me split right here. We're going to do step 3 over there. So step 2, assume n equal k is true. All right. So let n equal k. When n is equal to k, what we're getting is 4 times the sum from r equal 1. 4 times the sum from r equal 1 to k, because n is now k, of 5 to the r. And that is going to be equal to, that's going to be equal to 5 to the k, n is k now, so it's 5 to the k plus 1 minus 5. All right, and again, you assume that this is true. Assume it is true. Assume n equal k is true. Assume that it's true. All right, now let's go to step 3. Step 3 now, we need to show that n equal k plus 1 is true if n equal k is true. For n equal k plus 1, what we're going to get is 4 times, we're supposed to get 5 to the k plus 1 minus 5. So pretty much you need to get 5 to the k plus 2. All right, we need to get 5 to the k plus 2. So now for n equal to k plus 1, for n equal k plus 1, we're going to have that, we have 4 times the sum, 4 times the sum from r equal 1 to n of 5 to the r n equal k plus 1, sorry. Why am I writing n? N is k plus 1. So don't write the n, write k plus 1. So it's 4 times the sum from this. So r equal 1 to k plus 1 of this. All right. That's going to be equal to the sum from 1 to k. Remember, it's equal to the sum from 1 to k. So it's going to equal to the sum from r equal 1 to k of f of r of 5 to the r plus the k plus 1th term. The k plus 1th term is going to be you putting k plus 1 over here. So the k plus 1th term is going to be 4 times putting in k plus 1 here, it's 5 to the k plus 1. That's the k plus 1 term. All right. And so what this is working out to be now is the sum from 1 to k of 5r. We said that it's right here. It's 5 to the k plus 1. So it is 5 to the k plus 1 minus 5 plus 4 times 5 to the k plus 1. All right. Now look at this. You have 5 to the k plus 1 plus 4 times 5 to the k plus 1. So that is just 5. That's just 5 times 5 to the k plus 1. All right, you have 1 donut and you have 4 donuts. You add them and you get 5 donuts. So it's 5 times 5 to the k plus 1 minus 5. Now, according to laws of indices, this 5 is really 5 to the first power. So it's really 5 to the first power being multiplied by 5 to the k plus 1 minus 5. Now, whenever the bases are the same, we can add the powers. So whenever the bases are the same, we add the powers. So this becomes 5 to the k plus 1, 5 to the k plus 1 plus 1. So it's 5 to the k plus 1 plus 1. We add the powers, minus 5. And so therefore, n equal k plus 1 is true. So we can write our conclusion now. Therefore, n equal to k plus 1 is true if n equal k is true. Nice and easy, soft. So what do you finally conclude? Finally, you can conclude that hence by principles of mathematical induction, the statement above is true for all natural numbers. Nice and easy, soft. The statement above is true for all natural numbers. Nice and easy, soft. And that takes care of question number 1. Too easy. Let's move on now to question 2. Question 2 says the relation f is such that it maps set A to set B and set G is being mapped from set B to set C. They are functions which are both one-to-one and onto. Show that G of f is one-to-one